universe is not a quiet place. Out in the deep silence between the stars, cataclysms unfold that make every explosion on Earth seem like a whisper. We are about to journey through the 25 most powerful detonations ever recorded in the cosmos. You will witness stellar deaths that outshine galaxies, black hole eruptions that carve voids in space, and the primordial blast that started it all. We will measure their power not just by raw energy, but by the scales of their fury and how they forever changed our understanding of reality. By the end, you will know the stories behind cosmic events so violent they defy belief. How does a star's final scream echo across 12 billion years? What leaves a scar in the sky larger than 1,000 galaxies? The answers rewrite the story of our universe. What do you think it means to live in a cosmos built by such magnificent violence? Our list begins not with a bang in the void, but with the bang that created the void. The ultimate cosmic explosion is the Big Bang, the event that birthed everything we know. But to call it an explosion is almost misleading. This was not a fireball erupting into a pre-existing emptiness. It was the simultaneous and violent creation of space and time themselves. In a fraction of a second, a phenomenon called cosmic inflation caused the entire universe to expand from a point smaller than a single atom to a volume larger than our observable cosmos today. This expansion was not just space growing, it was space being created, carrying with it an unimaginable release of energy that would condense into the first particles of matter. All the stars, planets, and galaxies to come were forged in that first, incomprehensible moment of creation. We have a direct snapshot of its aftermath. About 380,000 years after the initial event, the universe had cooled enough for light to travel freely for the first time. That ancient light, stretched and cooled by the expansion of the universe over 13.8 billion years, still washes over us today. We detect it as a faint, uniform glow in every direction, known as the cosmic microwave background. It is the oldest fossil we can ever find, a baby picture of the cosmos, and it shows the tiny ripples in density that would one day grow into the vast cosmic web of galaxies. This event set the stage for every other explosion on our list, providing the raw material and the very arena in which all future cataclysms would unfold. That faint cosmic glow is our first piece of evidence, but it is not the only one. The universe carries the fingerprints of its explosive birth in other profound ways. Look at the galaxies around us. In the 1920s, astronomer Edwin Hubble made a startling discovery. He found that distant galaxies are all racing away from us, and the farther away they are, the faster they are moving. This is not because we are at the center of some cosmic retreat, but because space itself is stretching, carrying the galaxies apart like raisins in a rising loaf of bread. This observation, known as Hubble's law, is the direct echo of that initial expansion, the universe still inflating from the power of its first moment. Another crucial clue is written in the very atoms of your body. In the first few minutes after the Big Bang, the universe was a searing nuclear furnace. Conditions were perfect for the simplest atomic nuclei to fuse together from a soup of protons and neutrons. This primordial cookbook produced vast amounts of hydrogen and helium, with trace amounts of lithium. The predicted ratios of these light elements, calculated from the physics of that hot, dense state, match almost perfectly what we observe throughout the cosmos today. Every star, every planet, every molecule of water began as raw material forged in that initial fire. This is the true and lasting power of the Big Bang. Its explosion was not just a release of energy, it was the act of creation itself. It set the rules, provided the ingredients, and laid down the blueprint for everything to come. Every galaxy cluster, every swirling nebula, every rocky world orbiting a distant sun is a direct descendant of that event. While the explosions that follow on our list are spectacular and violent, they are all rearrangements of the pieces this first explosion created. The Big Bang is the ultimate benchmark, the foundation against which all other cosmic power must be measured. It is a theoretical framework supported by overwhelming evidence, rather than a single flash we can point to in a telescope. But that changes now. From this point of origin, we move to cataclysms we can actually see, events so bright they pierce the veil of cosmic history and momentarily outshine everything else in existence. From that foundational roar of creation, we fast forward billions of years to a single, focused scream of pure annihilation. In 2008, a satellite named the Fermi Gamma-ray Space Telescope was silently orbiting Earth when its instruments were suddenly and utterly overwhelmed. It had just recorded the most powerful explosion ever seen in the universe up to that point. A blast of radiation so intense, it redefined our understanding of cosmic violence. This event was designated Gamma Ray Burst 080916C. The numbers are clinical, but the reality is anything but. This burst of light had been traveling for 12.2 billion years to reach us. It erupted when the universe was only 1.5 billion years old, a mere infant by cosmic standards. In just a few minutes, this single event unleashed more energy than our sun will produce over its entire 10 billion year lifetime. To grasp that scale, picture our sun, a furnace that has powered life on Earth for billions of years and will continue for billions more. Now imagine compressing all of that energy, every single second of solar output for 10 billion years, into a brief, terrifying flash. That is the incomprehensible power of GRB 080916C. What natural engine could possibly generate such fury? Astronomers point to the death of a star unlike any in our current galaxy. This was not a typical supernova. The leading theory suggests it was a hypernova, the catastrophic collapse of a truly monstrous star, perhaps dozens of times more massive than our sun. At the end of its life, such a star does not just explode outward. Its core collapses directly into a newborn black hole. But the story does not end there. As material swirls into the black hole at nearly the speed of light, powerful magnetic fields channel some of the infalling matter into two jets that blast outward from the star's poles. These jets, moving at over 99.9999% the speed of light, punch through the outer layers of the dying star and erupt into space. If one of those ultra-focused beams happens to be pointed directly at Earth, we see it as a gamma-ray burst, a lighthouse beam of pure high-energy radiation, announcing the birth of a black hole across nearly the entire length of the observable universe. GRB 080916C was a direct hit from one of the universe's most powerful particle accelerators, a testament to the fact that even in its youth, the cosmos was already capable of staggering violence. That 12 billion-year-old scream from a dying star was a record holder for over a decade, a benchmark of cosmic violence. Then, in October 2022, the record was not just broken, it was obliterated. On the 9th of that month, gamma-ray detectors on satellites across our solar system, from Earth orbit to the far side of the sun, were suddenly and completely blinded. A wave of radiation so intense it saturated their instruments had arrived. Astronomers quickly gave this event a fittingly simple nickname: the boat, the brightest of all time. Officially known as Gamma Ray Burst 221009A, this was a blast of a different character. While the previous record holder was ancient and distant, the boat was a relative neighbor, erupting a mere 2 billion light-years away. That is still an unimaginable distance, but in cosmic terms, it is practically in our backyard. This proximity meant we were not just hit by its initial flash. We were given a front-row seat to its spectacular aftermath. For weeks, observatories across the globe and in space trained their eyes on the spot. They watched as the fading afterglow of the explosion, created by the jet slamming into the surrounding gas, shone brighter than most supernovae. The James Webb Space Telescope, the Hubble Space Telescope, and countless ground-based observatories worked in concert to dissect its light, searching for clues. What they found was deeply puzzling. The energy released was off the charts, challenging every existing model for how these jets form and accelerate. The leading theory is that we witnessed the formation of a new black hole from a star of almost mythical proportions, a star so massive and with such rapid rotation that its collapse funneled an unprecedented amount of energy into those deadly beams. The boat was not just brighter, it was fundamentally different, a new class of cosmic catastrophe that is forcing us to rewrite the physics of stellar death. The boat was a cosmic siren visible only to our most advanced technology, but history reminds us that the sky has spoken directly to humanity before. In the spring of the year 1006, a new star appeared in the southern sky that was so brilliant it cast shadows at night and could be seen clearly during the day. Observers from Egypt to China, Japan to Switzerland all recorded the same astonishing event. In the constellation Lupus, the wolf, a point of light rivaling the crescent moon suddenly blazed into existence. For months it remained visible, a silent, terrifying beacon that many interpreted as an omen of war, plague, or divine judgment. This was supernova 1006, likely the brightest stellar event in all of recorded human history. The sheer volume of historical accounts gives us a priceless record. Chinese court astronomers called it a guest star, meticulously noting its position and gradual fading over 3 years. An Egyptian physician in Cairo wrote that its light was a quarter of the moon's brightness and that it sparkled intensely. A Benedictine monk in Switzerland saw it as a wondrous sign, while an observer in present-day Iraq described it as a large circular body, 2.5 times the size of Venus. This global chorus of awe gives us a fixed point in time and space, a cosmic crime scene we can still investigate today. Modern radio and X-ray telescopes have returned to those celestial coordinates. There, they found the expanding wreckage, a bubble of gas over 60 light-years across, known as supernova remnant 1006. This beautiful, chaotic shell is the debris from that ancient explosion, still racing outward at thousands of kilometers per second. By studying its light echo and the composition of this remnant, astronomers have solved the mystery of what caused the spectacle. Supernova 1006 was not the death of a single massive star, but the total annihilation of a white dwarf. A white dwarf is the dense, Earth-sized corpse of a sun-like star made primarily of carbon and oxygen. In a binary system, this dead star can gravitationally steal material from a companion. When the stolen mass pushes the white dwarf over a critical threshold, about 1.4 times the mass of our Sun, a runaway thermonuclear fusion reaction tears through it in a matter of seconds. The entire star is vaporized in a blast of perfectly calibrated power, a standard candle so uniform that astronomers use similar explosions to measure the vast distances to other galaxies. The 1006 event was a particularly powerful and nearby version of this stellar detonation. The remnant it left is more than just a ghost. It is one of the brightest sources of high-energy radiation in our sky, a natural particle accelerator where shock waves from the ancient blast energize cosmic rays to nearly the speed of light. That silent, shadow-casting star our ancestors watched was the flashbulb of a stellar suicide, a titanic release of energy that left behind an invisible but seething monument. A reminder that the night sky holds memories of violence written in fading light and racing gas. That ancient guest star of 1006 was not a solitary warning. Just 66 years later, the sky delivered another, even more consequential message. In early November 1572, a brilliant new star appeared in the constellation Cassiopeia, shining so brightly it rivaled Jupiter. Among those who gazed up in wonder was a meticulous Danish nobleman named Tycho Brahe. Armed with the finest pre-telescopic instruments in Europe, he did something revolutionary. He measured. Night after night, he recorded the star's precise position and its slow fading over the next 16 months. His crucial finding: this new star exhibited no detectable parallax, meaning it did not shift position relative to the background stars when viewed from different points on Earth's orbit. This placed it firmly in the realm of the fixed stars, far beyond the orbit of the Moon. That single, careful measurement delivered a devastating blow to the Aristotelian worldview, which held that the heavens beyond the Moon were perfect, immutable, and unchanging. Here was direct, observable proof that the celestial sphere could change, and change violently. Tycho's supernova, as it came to be known, was a bomb thrown into the heart of ancient cosmology. We now understand it was another type Ia supernova, the thermonuclear detonation of a white dwarf star. But its legacy is far more than historical. Today, we can still see the aftermath. In radio and X-ray light, Tycho's supernova remnant is a spectacular, expanding bubble of debris over 20 light-years across. This chaotic cloud is a natural laboratory of extreme physics. The shock wave from the explosion, still racing outward at thousands of kilometers per second, acts as a colossal particle accelerator. It slams into interstellar gas, heating it to millions of degrees and hurling atomic nuclei to nearly the speed of light, creating cosmic rays that bombard our own planet. By studying this 450-year-old crime scene, we learn how elements forged in the blast are scattered into space to seed future generations of stars and planets. The true power of Tycho's supernova was dual. Its visible light shattered an ancient human dogma, helping to pave the way for the scientific revolution. Its invisible remnant, still raging in silence, continues to teach us how the universe spreads the very ingredients for complexity and, perhaps, life itself. The shockwaves from Tycho's supernova had barely faded from human memory when the cosmos delivered its final visible performance in our own galaxy. In October 1604, another brilliant new star blazed into existence in the constellation Ophiuchus, the Serpent-bearer. This time, the principal observer was a man whose name would become synonymous with the motion of the planets, Johannes Kepler. He watched the star with a keen, analytical eye, documenting its brilliance and its slow fade over the next year. His detailed observations, published in a book titled On the New Star in the Foot of Ophiuchus, provided a crucial dataset for the emerging scientific age. Kepler's supernova was a landmark event, occurring just a few years before Galileo would first turn a telescope to the heavens. It represented the last dying star in our Milky Way galaxy, to be seen clearly with the unaided human eye, a final farewell from an era when cosmic cataclysms were witnessed directly, without technological aid. We now understand this event, known as Supernova 1604, was likely another Type Ia supernova, the complete thermonuclear obliteration of a white dwarf star. But the story of its power is best told not by its initial flash, but by the spectacular mess it left behind. 4 centuries later, our most powerful X-ray eyes, like the Chandra X-ray Observatory, have peered into its heart. What they reveal is not a simple, symmetrical bubble. Instead, Kepler's supernova remnant is a chaotic, lopsided wreck. It is an expanding cloud of multi-million-degree gas, over 14 light-years across, that looks like a cosmic grenade went off inside a complex environment. The asymmetry tells a story of a violent death that was anything but clean. The explosion likely occurred in a region dense with gas and dust, perhaps material shed by the white dwarf's companion star before the final detonation. The blast wave slammed into this uneven environment, creating a remnant that is brighter and more deformed on one side, a testament to the resistance it encountered. In some areas, knots of silicon-rich debris, the elemental ash from the fusion inferno, are racing outward. In others, shock fronts are accelerating particles to near light speed. This intricate, beautiful chaos is the true legacy of the explosion Kepler saw. It shows us that a supernova is not a single, neat event. It is the beginning of a long, complex interaction between stellar debris and the galaxy, a process that churns, enriches, and shapes the interstellar medium for thousands of years. The flash that captivated astronomers 4 centuries ago was just the opening act. For 4 centuries, the Milky Way fell silent, offering no new stellar fireworks for the naked eye. Then, on a February night in 1987, a cosmic alarm bell rang. In a neighboring galaxy, the Large Magellanic Cloud, a star that had shone quietly for millions of years, suddenly decided to die. This was supernova 1987A, the closest and most scrutinized supernova of the modern scientific era. Its light, a mere 168,000 light-years away, reached Earth on February 23rd, first noticed by an astronomer in Chile. Within hours, observatories across the southern hemisphere and satellites in space swiveled to watch. For the first time, we had the full arsenal of 20th century astronomy. Neutrino detectors, X-ray telescopes, ultraviolet sensors, pointed at a star in its final catastrophic moments. And the star delivered a treasure trove of secrets. Just hours before the visible light arrived, underground detectors in Japan and the United States registered a tiny, fleeting burst of subatomic particles called neutrinos. This was the smoking gun. Neutrinos are ghostly particles that barely interact with matter. Trillions pass through your body every second without a trace. The only event violent enough to produce such a concentrated pulse is the core collapse of a massive star. Those neutrinos were the direct signal from the heart of the explosion, the moment the star's iron core, unable to support its own weight, crumbled into a dense neutron star. The visible flash that followed was just the shock wave finally reaching the surface, the star's outer layers blowing off in a brilliant fireball. But the surprises did not end there. As the initial glare faded, astronomers witnessed something unprecedented. The supernova lit up a pair of mysterious, glowing rings that had encircled the doomed star long before its death. These were not created by the explosion itself. They were hourglass-shaped shells of gas, likely ejected by the star in a slow, windy phase tens of thousands of years earlier. The supernova's ultraviolet flash, like a cosmic camera flashbulb, ionized this pre-existing gas, causing it to glow in a perfect, ethereal halo. This iconic triple ring structure became the defining image of the event, a beautiful and unexpected artifact of the star's earlier life. We learned the progenitor star was not a red supergiant, as most models predicted, but a blue supergiant named Sanduleak -69202. Its more compact size altered the timeline and brightness of the explosion, teaching us that massive stars can take unexpected paths to their demise. Today, nearly 4 decades later, SN 1987A is far from a cold case. We continue to watch in real time as the blast wave from the explosion, traveling at over 10,000 kilometers per second, collides with the inner ring of gas. This collision heats material to millions of degrees, creating a dazzling display in X-ray light and churning out new elements. It is a unique laboratory, allowing us to watch the aftermath of a stellar catastrophe unfold year by year, testing our theories of how shock waves propagate, how dust forms in the ejecta, and what ultimately remains at the center. This single event transformed a theoretical chapter in an astronomy textbook into a living, breathing, evolving cosmic event we can still touch with our instruments. Supernova 1987, gave us a front-row seat to a star's death, but sometimes the universe stages a rehearsal instead of the final act. In the constellation Carina, a star named Eta Carinae decided to put on a show that defied all expectations. In the 1840s, this already luminous star, one of the most massive in our galaxy, began to brighten dramatically. By 1843, it had become the second brightest star in the entire night sky, outshone only by Sirius, despite being over 7,000 light-years away. This was not a quiet flicker, it was a cosmic tantrum of epic proportions. For nearly 20 years, Eta Carinae raged, pouring out an amount of light comparable to a genuine supernova. Observers at the time, like the astronomer Sir John Herschel, watched in awe as this point of light rivaled the brightest planets. Then, just as mysteriously as it began, the star faded, dropping below naked eye visibility. It did not die, it survived. This event is known as the Great Eruption, and it was the ultimate supernova imposter. The star had undergone a colossal outburst, violently ejecting a vast amount of its own mass, but stopping just short of total self-destruction. The evidence of that violent performance is still on display. Surrounding Eta Carinae is one of the most beautiful and bizarre structures in the heavens, the Homunculus Nebula. This is not a remnant from an ancient explosion. It is the fresh debris from the 1840s event, still expanding outward. Shaped like a vast glowing hourglass or a cosmic peanut, the homunculus is made of twin lobes of gas and dust that were shot out from the star's poles at millions of kilometers per hour. Within this nebula lies enough material to make several copies of our Sun, all flung into space in a single protracted fit of stellar rage. So what caused such a violent, non-fatal explosion? Eta Carinae is not one star, but two, locked in a deadly 5.5-year dance. The primary star is a monster, estimated to be over 100 times the mass of our Sun, and it is incredibly unstable. Such massive stars burn their nuclear fuel at a furious rate, generating such intense radiation pressure that they constantly teeter on the edge of ripping themselves apart. The leading theory suggests that during the Great Eruption, the star's outer layers became so bloated and opaque that radiation could not escape, causing a tremendous buildup of heat and pressure. This eventually triggered a partial explosion, blowing off the star's outer envelope in a series of convulsions, likely influenced by the gravitational tug of its companion star. The system survived, but it was forever changed. Today, Eta Carinae is a ticking time bomb. It is so massive and unstable that astronomers believe its true supernova could happen at any moment on a cosmic timescale. That means it could explode tomorrow or in 100,000 years. When it finally does go, it will be a spectacle unseen in our galaxy since Kepler's star in 1604, and it may even produce a gamma-ray burst. For now, this stellar survivor and its beautiful, billowing nebula serve as a stunning reminder that in the cosmos, even the rehearsals can be utterly earth-shattering. While Eta Carinae staged a violent rehearsal, another star performed a magic trick with light itself. In January 2002, a faint, unremarkable star in the constellation Monoceros, the unicorn, did something bizarre. Over a span of just a few days, it flared with incredible speed, becoming 600,000 times more luminous than our Sun. For a brief moment, it was the brightest star in the entire Milky Way. Astronomers braced for a supernova, but then, just as swiftly, it faded away. The star, named V838 Monocerotis, did not destroy itself. Instead, it produced one of the most visually stunning cosmic phenomena ever witnessed, a light echo. This was not a traditional explosion blasting material outward. The leading theory suggests this incredible flash was caused by a stellar merger, a rare event where two stars, likely a red giant and a smaller companion, spiraled together and coalesced in a final, fiery embrace. Another possibility is a massive thermal pulse, a final convulsive helium burn in the star's shell that violently expanded its outer layers. In either case, the star released a sudden, intense pulse of light that shot out into space like a single, brilliant camera flash. The true spectacle began after the flash had passed. That initial pulse of light began traveling through a vast, ancient shell of dust that the star had shed in earlier, calmer epochs. As the light hit successive layers of this dust, it was reflected back toward Earth, but with a delay. The Hubble Space Telescope captured this process in a series of iconic images that looked like an expanding, ethereal bubble. What we were seeing was not an expanding shockwave of gas, but the actual wavefront of the explosion's light, slowly illuminating more and more of the surrounding cosmic debris. It was a three-dimensional time-lapse of the event, a delayed broadcast written on interstellar dust. The power of V838 Monocerotis was unique. It did not unleash the raw, destructive force of a supernova. Its power was that of an ultimate cosmic flashlight. For years, that one brief flash acted as a scanning beam, revealing the intricate structure and geography of the dust clouds, light years around the star in exquisite detail. It showed us cavities, filaments, and shells we would never have seen otherwise, turning a single stellar outburst into a multi-year exploration of a hidden landscape. This event reminds us that a star's most powerful statement is not always about how much it destroys, but what it reveals in its fleeting, brilliant wake. The flash from V838 Monocerotis was a gentle illumination compared to what came next. Our journey now takes us to a different class of stellar corps, one where power is measured not in fire, but in pure, invisible force. We are entering the realm of the Magnetar. A Magnetar is a type of neutron star, the incredibly dense remnant left after a massive star goes supernova. Imagine crushing the mass of our entire sun into a sphere the size of a city. That is a neutron star. But a Magnetar takes this insanity a step further. It possesses a magnetic field so strong it defies comprehension. If you brought a Magnetar halfway to the moon, its magnetic field would erase the data from every credit card on Earth. These fields are a quadrillion times stronger than Earth's own protective shield. They're so intense that they literally twist the star's solid iron crust, storing unimaginable amounts of stress. And sometimes, that stress snaps. On December 27, 2004, a magnetar named SGR 180620, located about 50,000 light-years away in the constellation Sagittarius, did exactly that. In just 0.2 of a second, it released a giant flare. This was not a broad, expanding fireball of light. It was a focused, vicious spike of gamma rays, the highest energy form of light. For that fleeting instant, this single, tiny object outshone the full moon in gamma rays, despite being 50,000 light-years distant. The energy it released in that half-second heartbeat was greater than what our sun has emitted over the last 250,000 years. The pulse of radiation was so powerful it had a measurable effect on our planet. It ionized the upper layers of Earth's atmosphere, significantly disturbing the ionosphere for several minutes. Satellites orbiting Earth were bombarded, their detectors momentarily overwhelmed by the cosmic static. Some spacecraft, designed to sense nuclear detonations, actually thought they had witnessed a nearby atomic blast. The cause of this cataclysm was a process called magnetic reconnection. Picture the Magnetar's impossibly twisted magnetic field lines, wound up like cosmic rubber bands. When the strain becomes too great, these lines suddenly snap and reconnect in a new, lower energy configuration. This violent rearrangement unleashes a torrent of energy, accelerating particles to near light speed and producing that devastating gamma ray flash. It was a stellar-scale magnetic earthquake, a testament to the fact that in the cosmos, raw magnetic force can be just as destructive as any thermonuclear fire. The Magnetar's magnetic fury is a silent, invisible power, but some stellar corpses announce their presence with a relentless, rhythmic beat. In the year 1054, a new star blazed in the constellation Taurus, so bright it was visible in daylight for 23 days and remained in the night sky for nearly 2 years. Chinese court astronomers called it a guest star, an ominous, celestial visitor. Half a world away, Native American observers in what is now the southwestern United States may have captured its image in a petroglyph, a star painted beside a crescent moon. This was supernova 1054, and it left behind the most famous and studied corpse in the cosmos, the Crab Nebula. Today, through any modest telescope, you can see its ghostly, filamentary glow, a tattered tapestry of gas expanding outward at over 1,000 kilometers per second. This beautiful wreckage is the textbook result of a core collapse supernova. A massive star, having exhausted its nuclear fuel, saw its iron core implode in a fraction of a second. The rebound shockwave blasted the star's outer layers into space, creating the nebula we see. But the true heart of the crab, and the source of its enduring power, lies hidden in the center of that chaos. There, spinning 30 times every second, is a pulsar, a city-sized neutron star with the mass of our sun. This cosmic lighthouse emits a precisely timed beam of radiation that sweeps past Earth with every rotation, a pulse we detect from radio waves to gamma rays. It is this pulsar, this spinning dynamo, that truly brings the Crab Nebula to life. Its intense magnetic field and rapid spin generate a fierce wind of high-energy particles, which stream out and slam into the surrounding nebula, causing the entire cloud to glow with a brilliant, eerie light. The crab is not a static monument, it is an active, high-energy engine, a natural particle accelerator in our cosmic backyard. For astronomers, it is the ultimate calibration source, a steady beacon studied across the entire electromagnetic spectrum. From the radio waves that trace its filamentary structure, to the visible light of its glowing gases, to the X-rays and gamma rays that scream from its turbulent heart, the Crab Nebula is a masterclass in stellar death and afterlife. It shows us that a supernova is not an ending, but a transformation, where a star's final act gives birth to an object of even more fascinating and violent power. The Crab Nebula's pulsar is a potent reminder of our sun's own magnetic nature, though on a far gentler scale. Yet even our seemingly placid star can unleash a temper that reaches across the solar system. In early August 1972, between the Apollo 16 and 17 missions, the Sun did exactly that. A massive sunspot group, a tangle of intense magnetic fields on the solar surface, became unstable. On August 4th, it erupted in a series of solar flares, culminating in one of the most powerful outbursts ever recorded in the space age. This was not a gentle increase in brightness. It was a catastrophic magnetic reconnection event, similar to a Magnetar's snap, but on a solar scale, where twisted magnetic field lines broke and reconnected, accelerating a torrent of radiation and charged particles to nearly the speed of light. The first sign was a blinding flash of X-rays and extreme, ultraviolet light that reached Earth in just over 8 minutes, instantly ionizing the upper atmosphere. This caused widespread radio blackouts, disrupting military and civilian communications across North America and the Pacific for hours. But the real fury was still on its way. Following the light came a coronal mass ejection, a billion-ton cloud of magnetized plasma blasted directly toward Earth. It traveled the 93 million-mile distance in a record 14.6 hours, a speed so astonishing it shocked solar physicists. When this solar hurricane slammed into Earth's magnetic field, it triggered a geomagnetic storm of extreme intensity. Auroras, normally confined to polar regions, were seen as far south as southern France and Texas. The rapid shifts in Earth's magnetic field induced powerful electrical currents in the ground, a phenomenon called geomagnetically induced current. These currents overloaded telephone lines, causing widespread outages, and even triggered the detonation of numerous naval mines off the coast of Vietnam, which had been sensitized to detect magnetic signatures from ships. For astronauts, the event would have been a dire emergency. Had a crew been in transit to the moon or walking on the lunar surface during that storm, they would have been exposed to radiation levels high enough to cause acute radiation sickness, potentially a fatal dose without the protection of Earth's magnetosphere and atmosphere. It was a stark, sobering lesson in our star's latent power. The 1972 solar flare serves as a benchmark, a warning shot across our bow. Yet it pales in comparison to what other stars are capable of. Astronomers have observed superflares on distant sun-like stars, events that release 10,000 times more energy than our largest recorded flare. If our sun were to produce such an event, it would not just disrupt satellites and power grids, it could strip away portions of our atmosphere and fundamentally alter the chemistry of our planet. The August storm showed us that the calm yellow disk in our sky is, in truth, a barely contained fusion reactor wrapped in a dynamic and occasionally violent magnetic personality. The 1972 solar storm was a stark reminder of our star's latent power, but history holds the record for a far more violent tantrum. On the 1st of September, 1859, amateur astronomer Richard Carrington was sketching a large group of sunspots in his private observatory in England. As he watched, two brilliant beads of white light suddenly erupted from the darkened region, intensifying for 5 minutes before fading away. Carrington had just witnessed a massive solar flare, a direct explosion on the sun's surface. He did not know it, but that flash of light was the herald of a catastrophe already racing toward Earth. Within 18 hours, the true force of the explosion arrived. A coronal mass ejection of unimaginable scale, a billion-ton cloud of magnetized plasma, slammed into our planet's magnetic field. The result was the Carrington event, the most powerful geomagnetic storm ever recorded. Its effects were both beautiful and terrifying. Night skies around the world erupted in auroras of crimson, green, and purple, so brilliant that people could read newspapers by their light at midnight. The shimmering curtains were seen as far south as the Caribbean and Colombia, near the equator, where the northern lights are never seen. Gold miners in the Rocky Mountains woke up thinking it was dawn and began making breakfast, but the celestial beauty masked a dangerous reality. The world's most advanced technology of the time, the telegraph network, was thrown into chaos. The geomagnetic storm induced such powerful electrical currents in the wires that telegraph operators received severe shocks. Papers in telegraph offices caught fire from sparks. Most astonishingly, in some locations, operators found they could disconnect their machines from the batteries and still send messages for hours, powered solely by the celestial currents flowing through the Earth. The storm had turned the entire planet into a giant, unwanted battery. If an event of that magnitude struck today, the consequences would be catastrophic, not curious. Our modern infrastructure is a global web of vulnerability. High-voltage power grids, stretched across continents, would act as giant antennas for the induced currents, causing widespread transformer meltdowns and blackouts that could last for months or years. Satellite communications, GPS, and financial networks would be severely disrupted or destroyed. Studies estimate the total economic damage could reach into the trillions of dollars, with recovery taking over a decade. The Carrington event was not just a historical oddity. It is a benchmark, a direct measurement of the explosive power our own star can muster. It proves that the most dangerous explosion in our cosmic neighborhood may not be a distant supernova, but a sudden, violent sneeze from the seemingly steady sun we see every day. The sun's flares are a local danger, but the solar system itself is a shooting gallery with far larger bullets. 66 million years ago, one of those bullets struck Earth, delivering an explosion that rewrote the history of life on our planet. This was the Chicxulub impact event. A mountain-sized asteroid, perhaps 10 kilometers across, slammed into the shallow seas of what is now the Yucatan Peninsula in Mexico. The energy released in that single instant was almost beyond human comprehension. It was equivalent to detonating billions of the nuclear bombs used in World War II all at once. The initial flash of heat ignited continent-spanning wildfires. The ground shock wave, traveling at the speed of sound, leveled everything for thousands of kilometers. Then, colossal tsunamis, hundreds of meters high, radiated out from the impact site, scouring coastlines across the globe. But the true killer was what the explosion threw into the sky. The impact vaporized billions of tons of rock, launching it on suborbital trajectories to rain back down as superheated debris, turning the atmosphere into a global oven. More critically, it pulverized the bedrock, ejecting trillions of tons of fine dust and sulfur aerosols high into the stratosphere. This created a perpetual global night. Sunlight was blocked for months, perhaps years. Photosynthesis ground to a halt, collapsing food chains from the bottom up. Temperatures plummeted in an impact winter. Acid rain fell worldwide. This cascade of cataclysms, all triggered by that one cosmic collision, led to the extinction of the non-avian dinosaurs and 75% of all species on Earth. The Chicxulub crater itself, over 150 kilometers wide and 20 kilometers deep, is now buried under younger rock, a hidden scar and a profound testament. This event frames explosive power in a terrifyingly intimate way. It was not a distant star dying. It was a piece of cosmic debris, a leftover fragment from the formation of the planets, carrying kinetic energy gathered over billions of years of orbit, and unleashing it in a single, world-altering moment. It reminds us that the universe's violence is not confined to the depths of space. It can travel silently across the void and knock on our door, proving that the energy to reshape a biosphere, to end one era and begin another, can arrive unannounced from the dark. The Chicxulub impact was a global cataclysm, but sometimes the universe sends a warning shot instead of a direct hit. On the morning of June 30th, 1908, in a remote part of Siberia near the Tunguska River, a brilliant fireball streaked across the sky. Moments later, a titanic explosion ripped through the air. The blast, equivalent to 10 to 15 million tons of TNT, flattened an estimated 80 million trees across 2,000 square kilometers of forest. The trees were not just knocked over, they were felled in a radial pattern, pointing away from a central point like spokes on a wheel, their tops stripped bare and their trunks charred. Yet, when expedition scientists finally reached the remote site 19 years later, they found no crater. The ground was scarred and burned, but there was no great hole in the earth. This was the central mystery of the Tunguska event. The leading explanation is a cosmic airburst. A relatively small stony asteroid or comet fragment, roughly 60 meters across, entered Earth's atmosphere at over 50,000 kilometers per hour. The intense pressure of plowing through our air at such speed caused it to heat up and explode violently about 5 to 10 kilometers above the ground. The resulting fireball and superheated shock wave did all the damage, vaporizing the object completely before any sizable pieces could reach the surface. It was a bomb that detonated in midair. The power of that single aerial detonation was felt around the world. Seismographs across Europe and Asia recorded the ground shaking as if from a major earthquake. Barometric sensors detected atmospheric pressure waves that traveled around the globe not once, but twice. For nights afterward, people across Europe and Russia reported strange, luminous skies and glowing clouds at midnight, so bright you could read a newspaper outdoors. Scientists believe this night glow was caused by dust from the vaporized object injected high into the stratosphere, where it reflected sunlight long after sunset. The Tunguska event stands as a powerful and sobering warning. It was not a dinosaur-killing impact. It was a far smaller, more common type of event. Yet if it had occurred just a few hours later, the rotation of the Earth would have placed it over a major population center like St. Petersburg or London, and the death toll would have been catastrophic. This single explosion over an empty forest demonstrated that we do not need a direct hit from a mountain-sized asteroid to face a global disaster. A much smaller rock, exploding unseen in our atmosphere, holds enough raw kinetic energy to devastate a region the size of a modern metropolitan area. It is a reminder that the cosmos does not always announce its violence with a crater. Sometimes it leaves only a whisper in the air and a forest of fallen giants. The Tunguska airburst was a solitary crack of cosmic thunder over a silent forest. 2 decades ago, we witnessed a full-scale symphony of impacts, not on Earth, but on the solar system's giant shield. In July 1994, the fragmented comet Shoemaker-Levy 9 performed a spectacular death dive into the atmosphere of Jupiter. This was not a single impact, but a string of 21 separate explosions over 6 days, as each mountain-sized chunk of the comet, torn apart by Jupiter's immense gravity on a previous pass, slammed into the giant planet one after another. For the first time in history, humanity had a front-row seat, with telescopes across Earth and in space trained on the predicted point of impact. The Hubble Space Telescope captured the event in stunning detail. As each fragment, some over 2 kilometers across, plunged into Jupiter's gaseous layers at over 200,000 kilometers per hour, it created a brilliant flash of light, a fireball hotter than the surface of the sun that rose thousands of kilometers above the cloud tops. These momentary novas were followed by the formation of enormous dark scars in Jupiter's southern hemisphere. Each impact plume ejected vast amounts of material from the deep atmosphere, which then rained down and spread out, creating bruises larger than our entire planet Earth. The energy released by each collision was staggering, with the largest impacts equivalent to 6 million megatons of TNT. To grasp that scale, the largest nuclear device ever detonated was about 50 megatons. The comet impacts were, individually, over 100,000 times more powerful. The dark scars they left persisted for months, visible even through small backyard telescopes, serving as a stark and humbling reminder. Jupiter, with its titanic gravity, acts as a cosmic vacuum cleaner, drawing in many such wandering objects that might otherwise threaten the inner solar system. Watching Shoemaker-Levy 9 strike was like seeing our planetary guardian take a bullet for us. It transformed planetary science from a theoretical exercise into a direct observation of cosmic violence on a scale we can barely fathom, proving that the solar system is still an active and sometimes violent construction site. Jupiter's violent welcome for that comet was a spectacle of pure kinetic force, but stellar explosions can also be precise, repeating, and strangely beautiful. In August 2013, a Japanese amateur astronomer named Koichi Itagaki was scanning the constellation Delphinus, the Dolphin, when he noticed a star that simply had not been there the night before. Within hours, the astronomical world confirmed his discovery. This was Nova Delphini, 2013, a new star that had suddenly ignited, quickly becoming bright enough to see with the unaided eye from suburban backyards. It was a classical nova, a very different kind of cosmic detonation from the total stellar annihilation of a supernova. This explosion did not destroy a star, it cleansed one. The drama unfolds in a binary star system where a white dwarf, the dense Earth-sized core of a dead sun-like star, orbits a living companion. The white dwarf's intense gravity relentlessly steals hydrogen-rich gas from its partner, This stolen material spirals down onto the white dwarf's incredibly hot surface, accumulating in a thin but growing layer. For decades or centuries, the pressure and heat at the base of this hydrogen ocean build silently. Then, a critical threshold is crossed. The hydrogen ignites in a runaway thermonuclear fusion reaction, a wave of nuclear fire that races across the entire surface of the white dwarf in mere seconds. The entire accreted shell of gas is blasted into space in a brilliant flash, outshining its host star system a millionfold. This is the nova. Nova Delphini, 2013, was one of the brightest in recent decades, a perfect example of this surface detonation. For a brief time, it shone as a beacon in the summer sky, a testament to a slow building theft ending in a sudden, violent purge. Unlike a supernova, the white dwarf itself survives the blast relatively unscathed. The cycle then begins anew. The dwarf's gravity goes back to work, stealing more gas, setting the stage for another explosion in the future. This makes novae recurrent events, cosmic time bombs that tick down over human lifetimes or centuries. While far less energetic than a supernova, a nova's power is still staggering, often releasing in its brief flare more energy than our sun will emit in 10,000 years. And they play a crucial role in the galactic ecosystem. The blast does not just eject plain hydrogen. The ferocious heat of the surface explosion acts as a nuclear pressure cooker, forging new, heavier elements like carbon, nitrogen, and oxygen in the stellar atmosphere before hurling them into the surrounding space. These enriched clouds of gas become raw material for future generations of stars, planets, and perhaps even life. Each nova is a sprinkle of cosmic fertilizer, a periodic reminder that even the smaller, repeating explosions in the universe are essential architects of complexity. The nova of 1885 was a quiet revolution in the night sky. On August 17th of that year, an amateur astronomer named Ernst Hartwig at the Dorpat Observatory in Estonia noticed something extraordinary. A new star of considerable brightness had appeared within the hazy, familiar glow of the great nebula in Andromeda. To the astronomers of the time, this nebula was believed to be a relatively nearby cloud of gas and dust within our own Milky Way. So when a star seemed to ignite inside it, they classified the event as a simple nova, a new star, and named it S Andromedae. It shone with the brilliance of a sixth magnitude star, visible through a modest telescope, before fading from view over the following months. This observation was filed away as a curious but not unprecedented stellar outburst. The truth, however, was far more profound. The astronomers of 1885 were looking at something no human had ever knowingly seen before. They were witnessing a supernova, the catastrophic death of a massive star, but not within our own galaxy. It was erupting in an entirely separate island universe, the Andromeda Galaxy itself, located 2.5 million light-years away. At that immense distance, for a single star to appear so bright to us, its explosion had to be of almost unimaginable power. S Andromeda was not a minor flare on a nearby star. It was a stellar detonation of titanic scale, outshining billions of its neighboring stars, combined for a brief, glorious moment. In hindsight, this event is a landmark of cosmic irony. It offered the first direct visual evidence that the universe was filled with galaxies beyond our own, and that the same violent processes at work in the Milky Way were also happening in those distant realms. Yet, the scientific framework to understand this was still 40 years away. It would take Edwin Hubble's work in the 1920s, using the new 100-inch telescope at Mount Wilson, to prove that Andromeda was indeed a separate galaxy and to measure its vast distance. Only then did the true nature of that 1885 nova snap into focus. S Andromedae was a message from a distant shore, a flare gun fired from another stellar city, telling us we were not alone in the cosmos. Its light had traveled for 2.5 million years to deliver that message. And we received it, but we did not understand the language until decades later. This historical oversight makes it one of the most significant explosions on our list, a quiet herald of a universe vaster and more violent than anyone at the time dared to dream. That quiet herald from Andromeda was a glimpse of stellar death in another galaxy, but a century later, we found a supernova that seemed to break all the rules of physics. In June 2015, an automated telescope network with a very long name made a startling discovery. The All-Sky Automated Survey for Supernovae, or ASAS-SN, is a robotic patrol of small telescopes designed to scan the entire sky for sudden changes. That summer, it caught a new point of light flaring in a distant galaxy. This event was designated ASAS-SN 15LH. And at first glance, it appeared to be a record-breaking supernova. Its peak brightness was staggering, outshining not just its host galaxy, but nearly every galaxy in the observable universe. It was 200 times more luminous than a typical supernova and 20 times brighter than our entire Milky Way. For a brief moment, this single exploding star shone with the light of over 50 billion suns. Astronomers immediately classified it as a superluminous supernova, a rare and poorly understood class of cosmic detonations that pushed the limits of known physics. But the true mystery of ASAS-SN 15LH was not just its brilliance, it was the source of that unbelievable power. What natural engine could possibly produce such a sustained, furious output of light? The initial and leading theory pointed to an extreme version of a magnetar. Recall those neutron stars with unimaginably strong magnetic fields. In this scenario, the core collapse of a very massive star would not just create a neutron star, but one spinning at breakneck speed, perhaps hundreds of times per second. This rapidly spinning, highly magnetized corpse would act like a cosmic dynamo, pouring a vast reservoir of rotational energy into the expanding shell of debris from the explosion. That injected energy would reheat the material, causing it to glow with that incredible, sustained luminosity. It was a supernova turbocharged from within by the spin of a newborn stellar corpse. But as more data came in, an even more exotic and terrifying explanation gained ground. Some astronomers began to suspect this was not a supernova at all. The light curve, the way the object faded over time, and the specific elements detected in its spectrum seemed to point toward a different kind of cosmic cataclysm. The alternative theory suggested we were witnessing the tidal disruption of a star by a supermassive black hole. In this scenario, a star similar to our Sun wandered too close to a monstrous black hole lurking at the center of its galaxy. The black hole's immense tidal forces, the difference in gravity between the star's near side and far side, stretched the star into a long, thin strand of gas in a process called spaghettification. This stream of stellar material then swirled into an accretion disk around the black hole, heating to millions of degrees and glowing with a ferocious light as it was slowly consumed. This interpretation would make ASAS-SN 15LH not a stellar death, but a stellar murder, an act of cosmic cannibalism on a scale so grand it mimicked the brightest supernova ever seen. The debate over this event's true nature continues, a testament to the fact that at the very edges of our understanding, the universe presents us with explosions so powerful they blur the line between different kinds of monsters. The debate over the nature of ASAS and 15LH shows our struggle to categorize cosmic violence, but sometimes the scale is so vast it simply defies categorization. In 2020, astronomers analyzing decades of data from multiple observatories made an almost embarrassing discovery. They found the largest explosion in the history of the universe since the Big Bang, and it had been sitting in plain sight for years, hidden because it was too big to see. The scene of the crime is the Ophiuchus galaxy cluster, a gathering of thousands of galaxies over 390 million light-years away, all bound together by gravity and swimming in a vast sea of superheated gas. This intergalactic gas, at millions of degrees, glows faintly in X-ray light. When scientists combined X-ray observations from NASA's Chandra Observatory with radio data and other surveys, they saw something bizarre. On one side of the cluster's central galaxy, there was a gigantic curved edge in the hot gas. It was not a ripple or a small dent. It was the border of a cavity, an enormous bubble carved out of the plasma. The scale is incomprehensible. This single cavity is over 1,500,000 light-years across. You could fit 15 Milky Way galaxies lined up end to end inside this one hole. The energy required to blow such a bubble in the thick, hot gas of a galaxy cluster is beyond staggering. Calculations show it required 5 times more energy than the previous record holder, and hundreds of millions of times more energy than a typical active galaxy produces over its entire lifetime. The source of this cataclysm is a supermassive black hole at the heart of the cluster's central galaxy. Unlike the brief, brilliant jet of a gamma-ray burst, this was an eruption of almost geological slowness and persistence. The black hole, feeding on surrounding material, launched a jet of plasma from its poles. But this jet was not a tightly focused beam. It was a slow, monstrous outflow that pushed into the cluster gas for tens of millions of years, like a cosmic blowtorch held against an unimaginably large wall of ice, slowly melting a cavern. The eruption is likely dormant now, a fossil of past activity. That is why it was so hard to see. There was no brilliant flash to catch our attention, only the lingering scar it left in the fabric of the cluster itself. This event redefines our understanding of power. It is not about a sudden flash of light, but about the slow, patient application of force on a scale that dwarfs entire galaxies. The Ophiuchus cavity is a monument to the fact that the most powerful explosions are not always the brightest. Sometimes they are the quietest, most immense absences in the sky. The Ophiuchus cavity reveals a black hole's slow, patient fury, but these monsters can also unleash their power in tightly focused, lightning-fast beams. Within our own galaxy, a system named Cygnus X1 demonstrates this on a smaller, yet no less violent scale. Discovered in 1964, it was the first object widely accepted as a stellar mass black hole, a corpse about 21 times the mass of our Sun, locked in a deadly dance with a massive blue companion star. Cygnus X1 is more than just a black hole. It is a microquasar. The name is a clue. A quasar is the incredibly bright core of a distant galaxy, powered by a supermassive black hole feeding on stars and gas. A microquasar is a scaled-down version, a stellar mass black hole or neutron star that mimics the behavior of its gigantic cousins. Here is how the engine works. The black hole's immense gravity relentlessly pulls gas from its companion star. This stolen material does not fall straight in. Instead, it spirals into a flat, superheated disk of plasma called an accretion disk, which glows fiercely in X-rays as it is compressed and heated to millions of degrees. But at the inner edge of this disk, something extraordinary happens. Not all the material crosses the event horizon. Powerful magnetic fields and intense pressures funnel some of the infalling plasma into 2 narrow jets that blast away perpendicular to the disk, shooting out from the black hole's poles at nearly the speed of light. These are relativistic jets, continuous, focused explosions of matter and energy. They are not a one-time detonation, but a sustained, high-velocity torrent. For decades, we could only infer these jets from Cygnus X1's X-ray and radio emissions. Then, in 2021, the Event Horizon Telescope collaboration, the same global network that took the first picture of a black hole's shadow, turned its incredible resolution toward this nearby system. While it did not image the jets directly, its data provided the most precise measurements yet of the black hole's properties and the fierce environment around it, confirming the violent dynamics at play. These jets act like cosmic blowtorches, punching deep into the surrounding interstellar medium. Where they slam into the tenuous gas between the stars, they create powerful shock waves that heat material and accelerate particles, often forming extended lobes of radio emission that resemble miniature versions of the giant lobes seen from quasars in distant galaxies. Cygnus X1 is a nearby laboratory for the most energetic processes in the universe, proving that the mechanics of a supermassive black hole powering a galaxy's core are, in essence, the same as those governing a stellar corpse just 6,000 light-years from Earth. Cygnus X1 shows us a continuous jet, but some stellar corps store their fury for a sudden, jarring release. Deep in the constellation, Vela, the sail, a cosmic lighthouse, spins with an almost perfect rhythm. The Vela pulsar is the crushed core of a massive star that exploded over 10,000 years ago. It rotates 11 times every second, and its lighthouse beam of radio waves sweeps past Earth with a precision that rivals the best atomic clocks. But this clock is not perfect. Every few years, without warning, it stutters. In a fraction of a second, the pulsar's spin suddenly increases. Its rotation speeds up by a tiny but measurable amount, an event astronomers call a glitch. These are not minor hiccups. They're explosive rearrangements happening deep inside the most extreme matter in the universe. The Vela pulsar is the champion glitcher, undergoing these sudden shifts more often and more dramatically than almost any other known pulsar. So what is happening inside this city-sized ball of ultra-dense matter? A neutron star is not a uniform sphere. Its outer crust is a rigid lattice of iron nuclei, while its interior is thought to contain a bizarre superfluid of neutrons, a frictionless quantum liquid that can flow without any resistance. This superfluid is supposed to spin at a constant rate, while the crust, slowed gradually by energy loss from radiation, spins a little slower. The difference builds up stress like winding a spring. The leading theory suggests that vortices in the superfluid, normally pinned to the crystalline crust, suddenly break free. When they unpin, they transfer a massive amount of angular momentum from the faster spinning interior to the slower crust in an instant. It is a stellar-scale earthquake, a starquake, that cracks the crust and jolts the entire star to a faster spin. The energy released in one of these events is staggering, equivalent to a magnitude 23 earthquake if such a scale existed. We do not just infer these glitches from timing data. The Chandra X-ray Observatory has given us a breathtaking visual of their aftermath. Chandra sees the Vela pulsar powering a magnificent jet of high-energy particles, a continuous stream shooting out from its poles. But this jet is not smooth. It is knotted and twisted, and observations suggest these structures may be tied directly to the glitch events. Each sudden internal starquake might send a powerful shock wave through the pulsar's magnetosphere, launching a fresh bullet of plasma down the jet and creating a visible knot that races outward at half the speed of light. Here, an invisible internal explosion writes its signature across light years of space. These glitches are a stark reminder that a neutron star is a dynamic, violent, and deeply strange object. Its perfect cosmic tick is maintained by a series of controlled detonations within, a balance of quantum forces and unimaginable density playing out in sudden, powerful snaps. The internal quakes of a pulsar are a whisper compared to the universe's most monumental collisions. On August 17, 2017, humanity's perception of the cosmos changed forever. Two gravitational wave detectors, LIGO in the United States and Virgo in Italy, felt a distinctive ripple in the fabric of space-time. It was not the deep thud of merging black holes they had heard before. This was a higher-pitched chirp, lasting about 100 seconds, the signature of two incredibly dense objects spiraling together. The signal was named GW170817. Crucially, the detector's triangulation provided a rough patch of sky. Within seconds, an alert shot out to astronomers worldwide. Less than 2 seconds after the gravitational wave arrived, the Fermi Gamma Ray Space Telescope detected a short, weak burst of gamma rays from the same general direction. The chase was on. Telescopes across the globe and in space swiveled to that patch of sky in the constellation Hydra. 11 hours later, a team using the SWOPE telescope in Chile found it. A new point of light in a galaxy called NGC 4993, about 130 million light-years away. This was the kilonova. For the first time in history, we had seen the same cosmic catastrophe with 2 completely different senses. We felt its gravity and saw its light. The event was the merger of 2 neutron stars, each the hyperdense core of a dead star. As they circled each other thousands of times per second in a final, fatal dance, they sprayed gravitational waves into the universe. In the last moments, they collided, likely forming a single, more massive neutron star or a black hole in a cataclysm that shook space-time itself. But the true power of this explosion was not in the collision's violence, but in its creative forge. The impact blasted a cloud of neutron-rich debris into space at a significant fraction of light speed. In this expanding cloud, a rapid series of nuclear reactions occurred, a process called rapid neutron capture, or the R process. Atomic nuclei were bombarded by a flood of free neutrons, building heavier and heavier elements in a matter of seconds. This single event forged a treasure trove of the universe's heaviest atoms. Calculations suggest it created an amount of gold and platinum equivalent to several hundred times the mass of Earth, along with other rare elements like uranium and neodymium. The light from the kilonova told this story through its color and evolution. It first glowed a hot blue color from the lighter elements, then over days shifted to a deep red infrared glow as heavier, opaque elements like gold and platinum formed in the cloud, blocking the inner light and re-emitting it at longer wavelengths. This was the confirmed birthplace of cosmic bling. The event also solved a long-standing mystery. The weak, short gamma ray burst that accompanied it proved that neutron-star mergers are indeed the primary engine for these brief, mysterious flashes of high-energy light. The multi-messenger campaign was a watershed. Observatories captured data from radio waves to gamma rays, painting a complete, evolving portrait of the explosion. We witnessed the birth of a new class of cosmic event, one that is both a destroyer and a creator. It revealed that the gold in your jewelry, the platinum in a catalytic converter, and the uranium that fuels nuclear reactors were all forged in the furious, neutron-rich debris of colliding stellar corpses. This single explosion rewrote our understanding of cosmic chemistry, proving that the universe's most valuable elements are minted in the most violent of banks. That kilonova forged elements across 130 million light-years. But a much closer star recently gave us a scare that felt intensely personal. In late 2019, the constellation Orion, the Hunter, began to look strangely unbalanced. Its familiar, fiery shoulder, the red supergiant star Betelgeuse, started to fade. For months, this brilliant beacon, one of the brightest stars in our sky, dimmed dramatically. By February 2020, it had lost over 2/3 of its usual luminosity, dropping from its typical spot among the top 10 brightest stars to barely within the top 20. The astronomical community and the public watching along buzzed with a single electrifying question. Was Betelgeuse about to go supernova? Located a mere 700 light-years away, this star is a cosmic neighbor on a very short fuse. It is a massive, aging red supergiant, a star that has already burned through the hydrogen and helium in its core and is now fusing heavier elements in a layered, unstable structure. It is a prime candidate for a core collapse supernova, an event that could happen tomorrow or in 100,000 years. The great dimming event felt like a countdown clock suddenly ticking louder. The prospect was both thrilling and sobering. A Betelgeuse supernova would be a historic spectacle, visible in broad daylight for months and casting shadows at night, rivaling the full moon. It would be the ultimate cosmic show, a front-row seat to stellar death. But the dimming was not the final act. As astronomers trained an array of telescopes on the star, a different story emerged. The Hubble Space Telescope and other observatories detected evidence of a titanic surface event. Betelgeuse likely experienced a colossal convective upheaval, where a massive bubble of hot plasma boiled up from its interior and erupted from the surface. This stellar belch ejected a vast cloud of material, perhaps many times the mass of our moon. As this ejected gas traveled away from the star, it cooled and condensed into a cloud of dust, partially obscuring Betelgeuse's light from our view and causing the dramatic dimming. It was a pre-supernova burp, not the final scream. By April 2020, the star had returned to its normal brightness, the dust cloud having dissipated or moved out of our line of sight. The event was a fascinating lesson in the final turbulent chapters of a massive star's life. It showed us that these giants do not die quietly. They convulse, eject material, and dim and brighten in their final millennia, offering us previews of the coming cataclysm. While the final explosion did not arrive, the great dimming gave us an unprecedented look at the pre-death throes of a stellar giant. It transformed Betelgeuse from a static point of light into a dynamic, heaving entity, a constant reminder that the shoulder of the hunter we see every winter is, in truth, an unstable bomb waiting to detonate. We are now watching it more closely than ever, knowing that the next dimming event could very well be the real thing, a countdown finale written in fading light. Betelgeuse's fading light was a personal warning from a single, unstable star, but our own galactic neighborhood hides evidence of a far greater, more ancient cataclysm. To find the final explosion on our list, you must look not at a point of light, but into the seemingly empty space above and below the Milky Way's core. In 2010, scientists analyzing data from the Fermi Gamma-ray space telescope made a staggering discovery. Emerging from the heart of our galaxy were two colossal, symmetrical bubbles of high-energy radiation. These Fermi bubbles are not made of stars or glowing gas we can see with our eyes. They are vast structures of gamma rays, each extending an astonishing 25,000 light-years from the galactic center. Picture this. Our entire Milky Way galaxy is a disk of stars about 100,000 light-years across. These bubbles, towering above and below that disk, stretch for half that entire distance. If our eyes could see gamma rays, the night sky would be dominated by two immense, faintly glowing orbs, a cosmic hourglass centered on the constellation Sagittarius. This is the lingering scar of a slow, persistent explosion that began millions of years ago. The source is almost certainly the supermassive black hole that resides at our galaxy's very heart, Sagittarius, a star. While it is quiet now, the bubbles are proof it was once a raging monster. Astronomers believe there are two possible triggers for this ancient outburst. One is a tidal disruption event on an epic scale, where the black hole tore apart and consumed an entire star cluster or an enormous gas cloud. The other is a prolonged period of intense feeding, where vast amounts of material swirled into an accretion disk, lighting up the galactic center like a quasar. In either scenario, the black hole would have launched twin jets or a massive wind of energetic particles from its poles. Unlike the tight beam of a gamma-ray burst, this was a broader, more sustained outflow, a colossal pressure wave that pushed its way out into the galactic halo, a sparse region of gas and dark matter surrounding the Milky Way's disk. That shock wave, traveling for millions of years, is what we detect today, It plows through the halo gas, accelerating particles to near light speed, and those particles, in turn, generate the diffuse gamma-ray glow that outlines the bubbles. We are living in the quiet aftermath of that explosion, looking up at the still expanding walls of a blast chamber we did not know existed until this century. The Fermi bubbles teach us a humbling lesson about our place in the cosmos. The most powerful explosions are not always distant events in far-off galaxies. One erupted right here, in our own home, and its echo still surrounds us. It is a permanent monument to a time when the gentle giant at our galaxy's center woke up, flexed its power, and forever changed the space above our heads. This journey has taken us from the first moment of existence to the silent scars surrounding our own galaxy. We have witnessed explosions that outshine galaxies, collisions that forge gold, and outbursts that dim the shoulder of a hunter. Each cataclysm, from the patient inflation of the Big Bang to the sudden snap of a Magnetar's crust, operates on a scale that humbles our human sense of power. They are the universe's most violent verbs: collide, merge, collapse, erupt. Yet in every case, the story does not end with destruction. These explosions are the universe's essential creators. The supernova scatters the heavy elements of life into the void. The kilonova mints the gold and platinum of future worlds. The black hole's monstrous eruption clears galactic gas, triggering the birth of new stars. Even the impact that ended the dinosaurs opened ecological space for mammals, and eventually, for us. We are not separate from this chain of violence. We are a product of it. The iron in your blood was forged in a dying star. The calcium in your bones was blasted into space by a supernova. The very atoms that allow you to wonder about the cosmos were delivered by explosions that occurred long before our sun was born. We live in a cosmos built by magnificent, necessary violence. It is a reminder that creation and destruction are two sides of the same coin, spinning in the dark. So tell us, which of these 25 explosions left you most in awe? Was it the ancient scream of GRB 080916C or the patient fury of the Ophiuchus cavity? Share your thoughts below, and if you want to continue exploring the deepest mysteries of space, make sure to subscribe. Our universe still has countless secrets waiting to